All right, so let's begin here with the first day of complex numbers. So the first day of complex numbers has us take a look at the imaginary number I. We've been a little bit familiarized with I. We ran into it in an example back when we were still in Unit 5. Today we're going to dive a little bit deeper into this idea of what is I. All right, so whenever we have numbers in math, typically we're always working with real numbers. Up until now, you've worked with real numbers. Real numbers include integers. Integers are numbers like 1, 2, 3, 4, 5, 0, -1, -2, -3, -4, -5. They're basically whole numbers, positive or negative, and the number 0. Okay, a rational number is any number that can be written as a fraction, essentially, right? So that could be in numbers like 3.33, right? That number could be written as a fraction, therefore it's a rational number. And then there's irrational numbers. So these are numbers that are still real, but they cannot be written as fractions. So for example, the number pi. We know pi, we know the approximation of pi, but if you know anything about pi, you know that pi does not repeat and it has an infinite number of values after the decimal. Okay, so there are other numbers like that are irrational, but that they cannot be written as a fraction. Okay, and then we have this other set of numbers, which is another realm of numbers, if you want to think about it, right? Like they exist in another dimension almost. It's these complex numbers. And complex numbers are made up of real numbers with imaginary numbers. Okay, but the imaginary numbers are what help create the complex. So we're going to look a lot at what imaginary numbers are, and imaginary numbers have the unit I. Okay, so you can see how all numbers that exist in math, you have the real numbers, and then you have the complex numbers. So within the real numbers, it's numbers that you've seen in math up until this point. And then as of today, moving forward, you're going to have to be familiar with the complex numbers, and that's where the imaginary numbers live. Okay, so they live within the group of complex numbers. Okay, so now let's talk about what I is. What is I? Okay, the number I is the basic element of the set of imaginary numbers. So I is what creates the foundation for all imaginary numbers. So the basic definition we have is that I is equal to the square root of -1. Okay, that is the definition of I. That is what I is equal to. All right. And when we learn about I, we also have to learn about, well, what happens if we take I to certain powers, such as power of 2 or power of 3 or power of 4. So I squared is a different value. I to the third is a different value. I to the fourth is a different value. Okay. But here's the reason why. All right. If we were to take I, and we know that I is equal to the square root of -1, how do we get I squared? Well, we would square both sides. So I squared is equal to, well, here we see that we have the square root of -1, but we know that if you square a square root, the square and the square root are inverses of each other. So you're left with -1. So we have another definition which tells us that I squared is equal to -1. Now, let's say we were looking to solve for what is I to the third. Well, I to the third is the same thing as I times I squared, right? I times I squared gives you I to the third. Well, I is square root of -1, and I squared is just -1. So if you multiply those two together, -1 is a constant. Remember that you do not multiply outside numbers with numbers that are inside the root. So this ends up just being negative square root of -1. And that's what I to the third is equal to. So that's where we get our third definition. Then we get to I to the fourth. You would agree that I to the fourth is the same thing as I squared times I squared. Well, what is I squared? I squared is -1. So this is like saying -1 times -1 again. And we get +1. So then I to the fourth is just equal to 1. And then once we've gone past I to the fourth, everything repeats itself again. So when we get to I to the fifth, I to the fifth is the same thing as I. Let's see, we have a question. Can I explain I squared? Is that what you mean? Yeah, okay. Well, okay, so if you have I, if you know that I is equal to the root of -1, and if you want I squared, you square both sides. So I squared now is equal to, well, what's the square root of -1 squared? Well, square root and square inverses. So they cancel, so what's left? -1. So I to the second power is equal to -1. All right. So watch how this works. Now when we get to I to the fifth, I to the fifth can be broken up into, well, you can see it there. I have it written I to the fourth times I. We know what I to the fourth is. I to the fourth is just +1, and I is the square root of -1. So 1 times the square root of -1 is just the square root of -1. So you can see how I to the fifth is exactly the same as just I. So it's just a cycle, right? It starts to repeat itself again. Guess what I to the sixth power is going to be? Well, if you were to follow the pattern, right, now that we cycled back, what is I to the sixth? Well, I to the sixth is I squared times I squared times I squared. Or it could be I to the fourth times I squared, right? Because the powers add up to 6. So let's say it's I to the fourth. Well, I to the fourth is just 1. I squared is -1. So 1 times -1 is just -1. So you see it cycles back. I to the sixth is -1. So these two are the same. All right, so the idea is that there's a pattern that if we ever wanted to find I to some power, it's either going to be I to the first, I squared, I to the third, or I to the fourth, because they keep cycling back over and over. All right, but the important part is understanding what I is, and that it's just square root of -1. And the other really important one is this one. I squared is equal to -1. Okay, I would say those are the two more important ones to remember. Everything else can be solved for. Right, so those are our big ones. Those are the big takeaway. What do you mean, Nelson? We could use odd values. Yeah, you could have done I to the third times I to the third. Yeah. I think it's a little bit more difficult, but you could have done it. So I like using like -1. I like using 1 because those numbers are easy to deal with. But if I have to work with negative square root of -1, right, that's a little bit more difficult. All right, let's move on to an example now. And this is where we're going to start to simplify these complex numbers. Okay, so we have seen things like this before, where we get to, let's say, quadratic formula, we have inside of a square root, we see a negative. A lot of times we would just say, oh, that's imaginary, and we would stop, right? We wouldn't continue to simplify. Now that we know that there is a value for negative inside of the square root, we're going to have to simplify. All right, so I want to talk a little bit about this property of exponents. I'm sorry, this property of square roots first, which says, question, what's I squared plus I to the fifth? It's not, you're not adding. No, 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 you're not adding. You're multiplying. You're multiplying. Like I to the fifth can only be generated by I to the fourth times I to the first because you add the powers to get 5. right? So it's almost like we separated, but I always multiplied them, right? There is no adding of I squared plus I to the fifth. In that case, those are like not like terms. It's like trying to add x squared plus x to the fifth. They're not like terms, so you can't add them. All right? Did that make sense for you? Got it? Okay. All right. So what is this trying to say? It's saying that if I have the square root of a product of two numbers, let's call those numbers a and b, I can also write it as the square root of a times the square root of b, right? Now, why is that relevant? Well, because I can think of square root of -3 could be the square root of -1 times 3. So then I can then use this property, which says if I have the product of two numbers inside my square root, I can break them apart into separate square roots. So I can actually have the square root of -1 times the square root of 3. Right? Do you see that? We broke it apart into those factors. I'm using -1 on purpose because what is square root of -1? It's imaginary. It's the unit I. Yeah, so now what I have is I times root 3. Okay, but the more common way that you see it written is square root of 3 with the I multiplied to the outside. Okay, that's why I left this here as a reminder that I goes outside of the square root, not inside. Really common mistake that I see a lot is kids write it like this. Okay, that would be wrong because I is already representing the square root of -1. So you don't want to say that I is inside because then that means you have another square root inside of a square root. And that's not the case. So this would be incorrect. The I needs to go outside of the square root. So I like to close my square root with a little drop down roof, kind of. And then my I is clearly outside of that. So the simplified version of the square root of -3, you basically pull the I out and change the number from a negative to a positive. Right? That's basically it. That's basically what we're doing. But we're using properties of square roots, and we're using what we know about the imaginary unit, which is I, to be able to simplify it. So this is our simplified version. Square root of 3 times I, which is on the outside. All right. Questions about that? Okay. Sounds good. Let's move on to number 2. Okay. So here's the hint. We have a larger number now, 98. Okay. The first thing you want to do whenever you do have a negative inside the square root is extract it. So I like to use the term extract, basically like pull it out. So what did we just learn? We learned that this square root of -98 could also be written as the square root of 98 times -1. And if we can write it as a product of two numbers, then you can split it up as the square root of 98 times the square root of -1. And then we know, hey, the square root of -1, that just becomes I. So now I have square root of 98 times I. But there's more that we could do to simplify, right? We need to simplify the square root of 98. And so how do we do that? Well, what we would like to do is do like a factor tree, right? Because what we're looking for is, can I find any pairs of numbers so that I can simplify this square root? So let's think about how we could do that. And this is what I like to do when I'm simplifying square roots. If I have 98 and I have a square root, It means I'm looking for a pair of numbers, right? Square root means, well, opposite of square. Square means two. So you're looking for two of the same numbers. Well, I need to break this 98 down, but unfortunately, it's not 49 times 49, right? That's not how we get 98. So we need factors, meaning numbers that multiply to be 98. Okay? Can you think of any for 98? A pair of or any two numbers that multiply to be 98. Oh, 14 times 7. Does that work? It does work. Okay, good. 14 times 7. All right. Now, when you're doing these factor trees, when you break down a certain number, I like to draw like a slash through it because that means I've already kind of factored that into two smaller factors. Now, when you look at a number like 7, 7 is a prime, meaning that it only divides into 7 or is only divisible by 7 and itself. So the only factors for 7 would be 7 times 1, but then we would get caught in like an endless loop. So if you get a prime number, you stop trying to factor it. However, if you get to 14, what are my factors for 14? Yeah, we have 2 and 7. And since I factored 14, I'm also going to draw a little slash through it. So what does this mean? It means that 98 in its most factored form is basically just 7 times 7 times 2. That's all it is. It's the product of those three numbers. So since I factored it down all the way, remember what the goal was? I was looking for a pair of numbers, looking for a pair. So I see a pair, even though they're on different branches, the pair of sevens. Okay, there's a pair of sevens. So how do we treat that? If there is a pair of numbers, that number gets pulled out of the square root. And the number that is by itself, right, has nobody, gets stuck inside of the square root. So we would leave the 2 inside. Okay. So square root of 98 is actually just 7 times square root of 2. And you might be wondering, like, why is that? Well, think about what square root of 98 is. Square root of 98 is 49 times 2. And we just talked about the fact that we could then break it up as the square root of 49 times the square root of 2. And look, square root of 49 is just 7. And so then that still just leaves you with that square root of 2. You bring the square root of 2 over. So that's why we end up with 7 square root of 2. But don't forget the fact that there was an imaginary already on the outside. So then this would be the most simplified form of the square root of negative 98. Okay. Let's see. What if there were 3 of the same factors? Okay, so for example, a number like 8. If you were to factor down 8, you get 4 times 2, and then 4 factors into 2 times 2. So we have a pair, right? But then there's still a 2 left over. Same way, the pair gets to escape the square root. And then the 2, this one, the boxed one, is the one that was by itself, has to go back inside the square root. So 8 is actually just 2 square root of 2. Right? Because 8 is also, right? If you're trying to take the square root of 8, square root of 8 is the same thing as square root of 4 times 2, which is then the square root of 4 times the square root of 2. And the square root of 4 is 2, but the square root of 2 stays the square root of 2. All right. So that's why whenever I see the pair is what gets pulled out, but only as one value. Just 1, 2. Right? The same way that this pair of sevens only gave me 1 7. It wasn't 2 sevens, it's just 1. And then whatever's left over, I box it. And that gets put inside my square root. Okay, so I just did 8 as like an example since somebody asked. But are there any questions here on example number 2? No? Okay. Let's try some more. Okay, the more we do, the easier it'll feel. All right, so we get to example 3. We want to simplify the square root of negative 48. Once again, the first thing you ought to do is to extract the I. So then we want to change this into square root of 48 times I, right? I'm just taking like the shortcut now. Now that we've seen it a couple times, all we literally need to do is we write I on the outside, and that negative that was inside the square root is gone. Okay, it just becomes a positive 48, but it's positive 48 times I, or root 48 times I. However, 48 can be simplified, right? The square root of 48 can be simplified. So let's go ahead and open up a factor tree. Somebody give me some factors for 48. Okay, you want to try 8 times 6? Let's do it. Okay, so we factored 48 into 8 times 6, put a slash through 48. All right, now what about 8? Yeah, it's 4 times 2, slash through 8. And then 4, since 2 is prime, 4 factors into the 2 times 2. So 4 is slashed. We also then have to break down 6. And the only factors for 6 are 3 times 2. All right, so now I'm looking for pairs, right? I'm looking for pairs. As long as they are on the branches of my tree, doesn't matter that they're like disconnected. So for example, this is a pair. That's good. But also this is a pair right here. Right? You see what I mean? Like they don't have to be connected. But all of these are my prime numbers. 2 and 3 are prime. If I can find a pair of prime numbers, then I get to extract them out of the root. Okay, so if my square root remains, the only loner I have is the 3. So the number going back inside will be 3. Now I have 2 pairs of 2. So let's say for the first pair, my first extraction, that's a 2. The second extraction, another 2. And then we would multiply these together on the outside. Don't forget your I. So what does this really become? Well, 2 times 2 on the outside, because there's 2 pairs, right? 2 separate pairs, that's 4 times root 3 times I. Okay. Here's another way that's probably will seem easier. If you would have taken 48 as 16 times 3, and then 16 is just 4 times 4, that's your pair right there. You see that? And then this is my box. So sometimes we don't see that though, right? We don't always see it in the most efficient way. Usually we break it all down into the smallest of numbers. But if I see a pair of 4s, right, you see how that's just, okay, that's 4 outside, that's my pair. And then I would have a square root with my loner, which is 3, 3 goes inside. So you see how these end up being the same, but we approach them a little differently. All right. But of course, since it was a negative 48 that we had started with, once we extract the I, this has to be my final solution, right? The final solution has to include I. All right. Any questions about that one? Okay. Um, what do you mean if we simplified that one further? You mean the one where I did 16 and then 4 times 4? it would have just given you the same thing as what we got the first time. Because 4 would have broken up into 2 times 2 and then 2 times 2 again. Then you have two pairs of 2's. You extract both of them. Then on the outside, it becomes 2 times 2. So it would have been the same thing. But there's only one correct answer. For any time you simplify a square root, there's only one correct answer that you can get. There's different ways to get there, but there's only one that you should end up with. All right. Correct. If you do it correctly, yes, it should result in the same answer. All right, and that's just because we factor numbers differently, right? You may have thought of 8 times 6, but you didn't think of 16 times 3, perhaps. Or maybe you would have tried 12 times 4. What else works? 24 times 2, right? There's a bunch of different ways to first factor the 48 down. But at the very, very lowest level, it's going to be 2 times 2 times 2 times 2 times 3. Okay, one level higher could have been 4 times 4 times 3. Right. So what this one does is it saves you time. Right. It saves you time because you can just stop at that pair of 4. It's nice to have a big pair because you know, like, oh, I don't have to waste time breaking it down further. I just grab my pair of 4. That's my pair. My 3 is my leftover. Kind of, yeah. Right. Correct. Yeah. All right, let's move on to number 4. Okay, now this one is a lesson on extracting I first. All right, we want to extract the I first anytime you are dealing with imaginary numbers. Because if you don't, okay, you can arrive at the wrong result. So let's begin by first extracting the I, and then I'll show you what happens if you don't extract the I. So with the square root of 9, square root of negative 9 times the square root of negative 25, this would become the square root of 9 times I times the square root of 25 times I. All right. We know what the square root of 9 is. We don't need to do a factor tree. What is the square root of 9? It's 3, right? So we get 3I times, what's the square root of 25? Yeah, it's 5. So we get 5I. So we have 3I times 5I. Would you agree that 3 times 5 is 15? And then I times I should be I squared. Right, just like any other variable, if you multiply x times x, it'd be x squared. So with I, it's the same thing. I times I is I squared. But what do you know about I squared? What is I squared equal to? And you might want to look up at box number 2. Yeah, I squared is actually equal to -1. So really what you're getting here is that it's 15 times -1. So your answer to this is -15. Right? This would be the correct way to approach this problem. You extract I first. Okay? Now, what would happen, let's say, if you did not extract I? Here's the wrong way. All right, and I'm only showing you because it's easy to do it this way incorrectly. Common mistake that'll happen if you ever run into a problem like this is students will say, okay, I know that I can multiply inside of a square root times the other inside of a square root. So what do? They multiply -9 times 25, and they get the square root of 225. And then when they take the square root of 225, they say, oh, that's 15. But that's not the correct answer, because the correct answer is actually -15, but you got +15. Where was the mistake? The mistake is that they did not extract I first. They just multiplied these two values together. This is allowable, but this is only allowable when these are real numbers. And right now, they're not real numbers. These are imaginary numbers, right? So this rule will only apply when you have real numbers. If you don't have real numbers, you need to extract the I first. So the way that we did it the first time. So this is correct. This is incorrect. All right. Any questions about that? Okay. And let's try to do one last one. All right. This idea of rationalizing. Okay. Now you may have heard of rationalizing when, let's say, maybe you have a square root in the denominator, but it also applies to this idea when you have maybe an I in the denominator too. Okay. So what could we do? Well, rationalizing would involve multiplying the denominator and the numerator by something in order to get the I out of the denominator, right? I'm trying to end up with a ratio where I is not in the denominator. So what I can do now is I can multiply top and bottom by the value of I, okay? Right? Why is that allowed? Well, I over I, if you think about it, is just one. I divided by I is one. So I'm not really multiplying by anything other than the number one. If I multiply by one, I'm not changing it. So I'm maintaining the integrity of the rational number, but I'm multiplying by I over I. Okay, why does that help? Well, think about it. Now I multiply 4 times I, that's 4I, but now I have 5I times I, and isn't that 5I squared? So now what we have is actually 4I times all over 5 times what is I squared? That's negative 1. So we end up with 4I all over negative 5, which is the same thing as negative 4I over 5. But what have we done? The goal was to remove I from the denominator, right? Even though we still have I in the numerator, that's okay. But we've been able to remove I from the denominator by using this precise tool called rationalize. Okay?